All right, guys, so we are going to continue talking about the direct stiffness matrix. What we covered earlier is basically how to establish a direct stiffness matrix for truss element, and we got an individual element, and we assembled that after we got the stiffness matrix in a global format. We assembled that throughout the whole structure, and we got the stiffness matrix for the whole entire structure. Let's take some examples because we wanted to get that stiffness matrix for members. We want to assemble them to get the stiffness matrix of the structure in order for us to determine the joint displacements for this truss. So we do have these two members of a truss that has a force applied at the end. And the question that's been asked is, find the displacement at this location. Later on, I'm going to ask, find the reactions here. And later on, I'm going to ask, find the forces in the members. But let's start with the deformation right here. So let's look closely what we're doing and what we're going to be doing later on in the computer and basically in our calculations. You identify the nodes with circular shape like that. So it's going to be 1, 2, and 3. That's the naming of or identifying the nodes. And then you're going to identify the members. So this is going to be member 1 in that box, and this is going to be member 2, as you can see right there. And you're going to identify the third thing, what is near and what is far. So from 1 to 3 right here is near to far. So this is the arrow right here from here to here. And this one is near to far. You can put it the way you want it, but let's be consistent later on when we solve the problem. So identifying the joints, done. Identifying the members, done. Identifying the near and far, done. Next is identify the degrees of freedom. I expect that since I have 3 nodes and each node has x and y, I will have 2 times 3, that's 6 degrees of freedom. Let's see. 1, 2, 3, 4, 5, 6. Usually I like to start with the degrees of freedom that I don't know what the displacements are. So I come at this end, I don't know what 1 and 2 are. So I'm going to start here, 1 and 2. And this is a pin support 3 and 4, and that's another pin support 5 and 6. I expect that the deformations here, I'm sure they are going to be 0. Deformations here are going to be 0, and these are the ones that we want. So what do you think the first step should be after that? What we really need to do is establish a stiffness matrix for the members. So for that member that we're having, which is member 1, let's see where is member 1. Member 1 is the horizontal member right there. And we are going to go find out the stiffness matrix in the global setup, which is 4 by 4. That needs lambda x and lambda x squared and lambda x, lambda y. And what is lambda x? It is cosine alpha or cosine phi, and lambda y is cosine the other angle. So one of them is the angle with the horizontal, and the other one is the angle with the vertical, or cosine of phi and sine of phi. It's the same exact thing. So what we're saying is the cosine of phi, which is lambda x, is x far minus x near over L. Let's see, where is x far? Go back to our truss. X far is right here, which is 20 foot. And x near of this joint, which is 0. Here we go. 20 minus 0 over the length, which is 20. So lambda x or cosine of 0 is 1. That's understood. Similarly, cosine of theta y or phi y or sine of phi means y far minus y near. So let's go here. Y far is 0. Y near is 0. Divide by the length, and that will give you 0 as well. And that means that the sine of the angle is 0, and that is expected. Also, we'd like to find out AE over L, which is, as you can see it right there, this is what you're going to be using. Plug them into this matrix that we had earlier, and that will give you the stiffness matrix. Is that in local coordinate system or global coordinate system? That one 4 by 4 is in the global coordinate system. As I told you earlier, we don't need to go through local stiffness and do the transformation. Go to the last step, which is the stiffness matrix of the member in a global format. Will that solve the problem, or I'm still missing something? I think we're missing the second element that we're having, And the second element that we're talking about is going to be member 2, as you can see right there. So member 2 right here, we're going to do the same exact thing, near and far. So x far is 20, x near is 0. Here we go, 20 minus 0 over the length of 25. The sign is y far. Y far is 0, and y near is, as you can see it right there, of 15 divided by the length, so it's going to give you negative sign. This is lambda x and lambda y, or cosine and sine. And you plug this into that matrix right here for the element number 2. But pay attention to something here, that we designated 1, 2, 5, and 6. Where is this coming from? Let's go back to the element. This is the element that we're talking about. At the near end, we have 5 and 6, and at the far end, we have 1 and 2. How about this one right here? I have 3, 4, 1, and 2. So we have the 3, 4, and 1 and 2, as you can see right there. And these are the other degrees of freedom. And the reason that we are putting this as label for the rows and columns, so that when we assemble them, automatically the computer is going to be adding the entities that belong to each other at the same spot. We assemble them and we find out that we have a global stiffness matrix, which is not going to be 4 by 4 like these elements. It's going to be 6 by 6, which has 1, 2, 3, 4, 5, 6 columns and 6 rows as well. This is 6 by 6 is the global stiffness matrix in the global coordinate system for the whole entire structures. And we established the equation, which is the left-hand side, Q equals K times delta. And let's pay attention to something. The deltas that we're having is delta 1, 2, 3, 4, 5, 6. 3 and 4 and 5 and 6, let's go to the structure and see where they are. 3 and 4, 5 and 6 are known to be zeros. However, 1 and 2 are unknown. So here we go. We have 3, 4, 5, 6 displacements are 0, and these 2 are unknown displacements. However, that corresponds to Q1 and Q2 and then Q3, 4, 5. What is Q1 and Q2? These are the known forces at 1 and 2. And the rest are going to be the unknown. Let's go back. At degree of freedom 1 and 2, do we have any force in the x or in the direction of 1? No, 0. How about in the direction of 2? I have something of negative 30. So here we go. So we have 0 and negative 30 for that first part right here. And the rest are the support reactions. Q3, Q4, Q5, Q6. Where are they? In our example, reaction at 3, reaction at 4, reaction at 5, reaction at 6, as you can see right here. What is the beauty of this matrix? It's a very complicated one, but if you do that dotted line as partitioning after 2 rows, in that case, I can simply say that submatrix equals this submatrix times this one, delta 1 and delta 2, plus the second one right here times this displacement right here, which is going to be zeros anyways. From that, you can find the displacement delta 1 and delta 2. So let's see what we're getting. Here we go. We isolated that part, which is, as you can see right here, this is the K, and this is 0 and 30, and this is delta 1 and delta 2. Let's get back and see whether we got it right or not. Here we go. 0 and 30, and then this is what we call it now K1, 1. Multiplied by this displacement, and then this is K1, 2 times zeros. Here we go. So basically, that is the force, and this is K1, 1 times the displacement plus zeros. So if you solve this, that will give you the displacement of negative 16 at degree of freedom 1, and the displacement as negative 0.547 at degree of freedom 2. Perfect. So we achieved the first goal. See, this is the beauty of that method, that we are able to find the deformation of a truss in X and in Y in global coordinate system. The second step is, how can I find the support reactions? All you need to do is go and find out the support reactions by going to this sub matrix, that one right here, which is what we call Q3, Q4, Q5, Q6. This is 1 equals to the sub matrix that we're having there. So that's going to be 1, 0, 0, 0, negative 6, 4. Where is that here? Here we go. That part right here, which is K21 multiplied by delta 1 and delta 2 plus K22 times this part. So again, clear your mind and just imagine that this big matrix is composed of 4 pieces. K11, K12, K21, K22. Correct? In order for you to find the displacement, we said that forces that they are known equals K11 times this displacement. Done. In order for us to find the reactions, we say this forces right here equals K21, which is this matrix, submatrix, multiplied by the displacement. And of course, the second one, which is K22 times 0. We ignore that. And here we go. This is what we have, and we came up with this forces. So we have 40 kips in Q3, 0 in Q4, negative 40, and 30. So for this structure, remember 40, 0, negative 40, and 30. So 40, 0, and 2 other values that you're having, negative 30 and 40. That's basically what we ended up doing. So what we accomplished now is getting the displacement and getting the support reaction. Let's go over it again. So I'm going back. Here's the truss. Your initial thought of how can I find the displacement? Step number 1, identify the nodes, 1, 2, 3. Identify the members as 1 and 2. Identify the near and far, and then establish stiffness matrix for member 1. Establish the stiffness matrix for member number 2. And then assemble them. That's what we did. Stiffness matrix for 1 in a global coordinate system. Stiffness matrix for 2 in a global coordinate system. And then assemble them to find the global stiffness matrix for the structure. Once you have the global stiffness matrix for the structure, do partitioning. Where do we do partitioning? Whereby you have known forces and unknown displacements. So you come after 2 rows, after 2 columns, and divide that matrix into 4 parts. The first one in the left-hand corner, left hand at the top corner right here is K11, and that is K12, K21, and K22. Your target is to find the displacement. So all you need to do is say Q1 and Q2, which is 0 and negative 30, equals K11 times delta 1, delta 2. Done. Here we go. And you came up with delta 1 and delta 2, as you can see. If you would like to find the support reactions, you come and say that Q3, 4, 5 equals to K21 multiplied by delta 1 and delta 2. Here we go. This is what we did, and we came up with the support reactions, as you can see right there. And we're saying that the minus sign that we're having here, indicating that the forces or the displacements is opposite to what you assumed the arrows, the direction of the arrows at the joints. All right? What's next? I think what's next is to find the force in the member. So if you would like to get the force in the member, basically you can relate the local displacement and the global displacement, and you can substitute the force in the member basically as such. So you were able to figure out the displacements at the near and the end in a local format, as you can see right here, delta 1 and delta 2. And then you can find the force using the equation that we have for the force member, and that will give you the member force. And it turned out that the bottom member, the horizontal member, is subject to compression of 40 degrees kips with a negative sign, and that is exactly how you can use it to find it. So we accomplished 3 things: nodal displacements, reactions at the supports, and forces in the members. We're done with that example, as you can see right here. After you do force in the second member, it turned out to be 50 kips in tension using this equation as well. I would like to give you another example, and I was inclined more towards giving you this as an example that you can solve. It has 3 members in this case versus 2 that we had earlier. Pretty much the same exact scenario. You're going to identify the nodes right here and the members 1, 2, 3, and then you start solving them. So let me go through it very quickly and just ask you kindly to do it by hand, knowing that we have K1 and K2 for the members equals 250. So they gave you the AE over L already as 250. And for the member number 3, you had this to be a little bit stronger. It's 500 kips per inch. So basically, you know what the stiffness matrix, or rather the AE over L for each member is. What are we trying to find? Again, we find displacement, we find the reactions, we find the forces in the member. So we have a pin support right here and another support at the top. First step is, for member 1, you find out the stiffness matrix for member 1. So basically, member 1, as you can see right here, and I like that method more because it makes a lot of sense. This is a near and this is a far. So I have 4 and 5, 1 and 2, and I have it like that, 4, 5, and then 1 and 2. Very clear and straightforward for this member. And you have this. But before you do that, you have to find the cosine and the sine for that. Horizontal cosine of 0 is 1, and the sine of 0 is 0, as you can see. So you can construct and establish the stiffness matrix of member 1 in a global format. Done. How about member number 2? What do you think the cosine is and the sine is? The cosine of this is 0 because it's 90 degrees. The sine of 90 is 1. So here we go, 0 and 1, as you can see right here. And you construct the stiffness matrix. Let's pay attention. The red arrow, or the arrow that we're having here, start from that point to this point, right? So from 4, 5, and over there is 6 and 3. So let me go back one step. Why this is 3? This is a pin support and this is a roller support. The smart way of doing things is start with the unknown displacements first. So I started with 1 and 2 because there is no support here. They are free to move, so 1 and 2. Is there any other degree of freedom that I'm missing that can move and I don't have any ability to identify how much is it? Yes, the roller support at the very top at joint number 3 is allowing vertical movement. That's why we had here at the very top 3. So I have 1, 2, and 3 are the degrees of freedom that they are unknown, unidentified. We don't know exactly where they are and how much they are and all this stuff. But the others, which is 4, 5, and 6, that they are 0. Degrees of freedom equals 0. So let's see. The near x is 4 and the y is 5. So at the near x and the near y, 4 and 5. Here we go, 4 and 5. At the top joint there, what is the x for the far? It is 6. And what is the y? It is 3. That's why we have 4, 5, 6, 3. Near, far, I'm sorry, x and y for the near, x and y for the far. And that will determine that stiffness matrix for member number 2. I need your help here, guys, with member number 3. So member number 3 right here, where is the beginning? The one at the top, at joint 3. Where is the end? Right here, at joint 2. So let's see, what is the x and y for the near? 6 and 3. Here we go. 6 and 3. How about the far? 1 and 2. Here we go. 1 and 2. And that will establish the stiffness matrix of the third member, knowing that it's inclined and you have 0.6 and negative 0.8 as cosine and sine of the angle. This is essential because now you can add apple to apple or just add things correctly. So if I'd like to have 5 and 5, you can take column 5 and row 5, that will give you 0. And here, column 5 and row 5, that will give you 250, and so on. So you can assemble those easily. The labeling is going to be very essential so that you can add things together. And what do you think when you add them and assemble the global stiffness matrix for these three members, for that truss? What is the size going to be? Let's see. You have 3 nodes, 2 degrees of freedom at each. So is it going to be 6 by 6? Let's see. We ended up with having 6 by 6 stiffness matrix for the structure. That is absolutely right. And the left-hand side right here is the force. Right-hand side are the displacement. Let's see the force. Displacement 1, 2, and 3 are unknowns, and you have some forces. Let's go back to the structure. Displacement 1, 2, and 3 are unknown displacement. Do we have any force at 1? It is 0. At 2, it is negative 40. At 3, we have 0. That's why we have 0, negative 40, and 0. Correct? If you would like to solve this, what do? Partitioning. Remember, before we partitioned at 2, after 2 rows and 2 columns. Here we are going to partition at what? 3. So you can have a partition right here after 3 rows and after 3 columns. And then you can have this top left corner right here as K11. This is the 1. Multiply by delta 1, delta 2, delta 3 equals to the force, which is 0, negative 40, 0. Solve those. That will give you the displacements, negative 0.12, negative 0.375, and negative 0.16. These are the displacements that you expect for this truss. And then you plug them back here, and you solve for the forces or the support reaction, which is F4, F5, F6. How do we do that again? We take that submatrix right here, equals K2, 1, multiply by these deltas right here. Here we go. The forces F4, F5, F6 equals the 3 by 3 submatrix, which is right there, multiplied by this displacements right there. And when you solve this, you are able to find this force reactions F4, F5, F6. So we achieved 2 goals now for this truss. We were able to find displacements, delta 1, delta 2, delta 3, and we were able to find support reactions. Are we done with that, or we're still missing something? I believe we need one more thing. If we are ambitious, find the forces in the members. So isolate every member and say that I would like to check member 1, which is the horizontal member, right here, and you apply the equation that we're having for the force in the member. And bear in mind that might be this small q sometimes, a big Q sometimes, but don't get confused. This is the matrix that you're using for the forces, and it turned out to be negative 30 for this member. You repeat it for the vertical member, and you find out you have negative 40 for this member using this method or any other method that I listed in my presentation. And for the third member right there, you ended up with a positive tension force, as you can see right there. So with that being said, you are done with this example, and you are able to find the forces in the members. So I think that helps that you had the previous lecture was pretty much how to establish and assemble the stiffness matrix of this whole entire truss. And this one is giving you these 2 examples that you can assemble the stiffness matrix for the truss and solve for the delta and solve for the forces in the members. Later on, we're going to be just talking about this member, but I'll give you this as an assignment that you can start working on, and that is pretty much similar to the first example. All I need you to do is assemble this and find the stiffness matrix for this, and then this is K1 and this is K2, and then get the overall stiffness matrix. Do it by yourself, and then I'm going to send you an email with these slides so that you can have something to check your answers with. And then do me a favor and apply 2 KIPs at the very end right there, and start finding the deformation at this end and the support reactions and the member forces. Again, your assignment is establish the stiffness matrix. That's number 1. Number 2 is find the deformations at this node. Number 3 is finding the support reactions. Number 4 is getting the member forces. With that being said, I think that we are done with the truss stiffness matrix, how to do it by hand. to establish those and find all the unknowns of displacements and reactions and force members. And then later on, we're going to move on to a new topic, which is going to be beams. And then we're going to move on to a new topic, which is going to be frames. I'm going to assign something. This I'm going to be assigning it online. I'm going to send it to you, and I'm going to assign something for the computer program as well to do the same exact example using the computer and then compare these answers using the STAD software and using the hand calculation. With that being said, thank you so much, guys, and I'll see you next time. Thank you.